Cellulose is a great polymer that has one main drawback. It doesn't melt. Therefore, it is difficult to process into desired shapes, which is usually done by dissolving it. But in this presentation, I would like to show you how fibrillated cellulose itself can be shaped into beautiful three-dimensional patterns that completely change its surface properties. Microfibrillated cellulose, or MFC, is one of the most important structural units in vegetal biomass. On the top left corner, you can see the tempo-oxidized MFC suspension that I use in my work, with an average width of 11 nanometers. When you filter and hot press this suspension, you obtain a transparent film such as the one beside it. This film displays great mechanical, optical, and barrier properties, mainly due to its low porosity, as you can observe on the SEM image below. You can also notice that its surface is flat. Therefore, due to the hydrophilic nature of cellulose, it exhibits a low contact angle of 33 degrees, while the water penetration in the film remains slow due to the dense bulk. This material is neither water resistant nor water absorbent. In our research group at UBC, I have developed a technique to modify the surface of the same films to shift from a flat 2D surface to three-dimensional shapes, such as the pattern displayed on the top right-hand corner. This technique, microtemplating, simply relies on a modification of the MFC suspension flow during filtration and can result in a great variety of shapes. In this particular example, the film surface is now composed of regularly aligned flower shapes. When zooming in, we can see that the thin edges of these flowers are composed of vertically aligned individual microfibrils. This greatly increases the specific surface area of this multi-scale surface. The combination of the flower shape that creates capillary forces and the high specific surface area greatly improves the water penetration in the film. It now absorbs water in less than a second, as you can see on the image below, in a super hydrophilic fashion. This behavior can find applications in water harvesting, of course, but fluids transport in general. There is also potential to reach super hydrophobic properties by using patterns with lower dimensions, which is our current focus. But this technique is also much cheaper and more scalable than most techniques used to modify material surfaces. Nanolithography, for example, can cost up to several thousands of dollars per square meter, whereas microtemplating costs less than $1 per square meter. This paves the way to cost-efficient, advanced applications, such as anti-reflective surfaces, tribogenerators, and haptic devices. We are only beginning to explore the variety of shapes and properties it can offer to make microtemplating cellulose a great way to produce functional materials. Thank you very much.
Thank you.